Thanks. What I'm going to do today is try to do a quick run through of the genesis of this product, the Rattler. It's a radio-controlled truck that thank you. It's very maneuverable. It's 10-wheel drive. It can climb a 8-inch vertical obstacle like a cinder block. You can see all the wheels are driven, and it's fully articulated, and it's really cool. And the way that this, basically what I'm going to do is I'm going to use the timeline of the development process as a framework for the lecture. To start with, a lot of toys start out as inventions. Independent people, there are companies that make their living just inventing toys. They'll invent 100 toys in a year and sell 3 and be in business. And this product was like that. An inventor group came to our company with this invention right here, which basically worked on the video anyway. I never saw it work. It had self-destructed by the time I saw it. And so, but it proved the principle. It proved that you could have a 10-wheel drive, articulated vehicle that would basically work, and they had a very dramatic video to show it. The problem is that nothing about this is producible, cost-effective, safe, manufacturable, or anything. It's strictly a hand-built prototype with hundreds of dollars of parts in it, and nothing about it is toy-like. It's completely hand-built. There's a lot of different reasons why this isn't manufacturable. They used open U-joints to connect the segments. You can put your finger in there and crunch it like a nutcracker. They used a speedometer cable to drive all 10 wheels using worm gears. Speedometer cable is not toy technology. It saps a lot of energy, and worm gears are not appropriate for high speed. They're a high friction, high reduction type of drive, and when you want a high-speed vehicle, you don't use that. The efficiency of worm gear is very poor. You want a more high-efficient gear train. So that's why it's self-destructed. This thing weighs a ton. It uses high-end RC, hobby RC motor, high-end hobby RC battery pack, electronics. Everything is expensive, and it still barely works. So my job was to take this vision and turn it into a manufacturable product. And the starting point for that is always to establish your design parameters. To start out with, marketing and sales gets together and says, will this sell? They see the video and they get excited, but then they have to decide, well, anything will sell at a given price. What is that price? If it was free, of course, you could sell a lot of them, but if it was $300, you probably wouldn't sell any. So marketing comes up with a retail price that they're looking to hit. And in this case, the retail price was, well, I won't write it down, $80 they wanted it to sell for. And since it's a TV item, the retail doesn't take very much mark, so we could sell it to retail for about $65 if they're going to sell it for $80. Now, for us to sell it for $65, we have to buy it from the factory for about a third that. So a little over $20 is what we have to be able to make it for. So that becomes the target cost for me, is that I have to accomplish this with $20. And so my job is to first do some conceptual brainstorming and to think, can I even think of a way to make this possible? I can't use worm gears, I can't use speedometer cables, I can't use these killer U-joints. Is there a way to do it? And I came up with a couple of ideas of what I could do, and worked with marketing to come up with realistic performance parameters. I thought we could climb things pretty well. We chose some speeds. They wanted to be very powerful but very fast, so that we decided to go with a 2-speed gear train to accomplish those opposite goals. And basically, I tried to come up with a strategy that would make this thing possible. Let me get this part here. And there are a few basic things that I came up with, which, whoops, lamp on. How come the lamp's not on? There it goes. One major idea that I came up with was to use a ball joint effect where the segments would be connected. It's not a good. Segments would be connected by these ball joints. So you can see in this one, I have a ball joint attached to the upper housing. It's molded right in, and then the lower housing has the other half of the ball joint. And the same thing happens on the next one. So we have these integrally molded ball joints, and what they allow is the articulation without the pinching problem. And they also, another problem with that sample was that it would break, and this provides a rugged way to connect the segments. The other principle was to put universal joints concentrically within the ball joints. So you have within the centered on each ball joint is a universal joint. So that as the ball joint articulates, the center of the since the center of the U-joint is coincident with the center of the ball joint, everything is happy. And another major, the biggest innovation that I came up with to make this possible, I was sitting in my office thinking about this, and a word jumped into my head: hypoid gears. I don't know where I heard that before. I think I heard it in Professor Phelan's mechanical design class. And believe it or not, I actually reached up on my shelf and grabbed out my design book from Professor Phelan's class and flipped to the index to hypoid gears and started reading about hypoid gears. And it said that they were efficient, strong, appropriate for high-speed use. They're used in the rear differentials of rear-wheel drive cars, have been for about 50 or 60 years or more. And the key thing, however, is that with a hypoid gear, the shafts are not coplanar. I don't know if you can see it. Yeah, you can see it in here. That you can see that the axle shaft and the drive shaft actually cross each other. So that what that allowed me to do was to use a continuous drive shaft in each segment. And because one of the major problems here is how do you transmit all that torque from a single motor out to all those wheels without having all kinds of buildup of weakness and lash and things like that. And the hypoid gear, unique among gears that turn 90 degrees like this, have non-coplanar shafts, and that was the major breakthrough. The problem with hypoid gears is that they're hard to make. You can't just buy them off the shelf. But that's another story I'll get into in a second. So what I did is I prototyped the hypoid gear by modeling it in Pro Engineer. And this is a screenshot of what the model looks like. You can see the non-coplanar shafts there. And using the Pro Engineer data, I created a stereolithography model of a gear. And we took that and I lapped it in with another gear to make it smooth, and we made castings. This is urethane casting of the original, so we could get multiple gears. The other thing that I did was I designed a single segment. I just have the top half here. This is a very crude, rough thing with no detail, but it embodies the ball joints. And I also designed these are original stereolithography parts. This yellowish material is what it looks like when you get it. Also designed a bearing housing for the hypoid pair, and duplicated that. And then we made castings and duplicates of this housing to make 5 sets so we could build a prototype. And the reason, and the principle of the prototype is to try to prove out whether this is going to work, check your gear ratios, and see what speeds you can attain. This is another crude hand model that I had made actually before anything else, just to check the idea of the ball joint and check the travel, and also check this other weird idea I had. I had this idea that if we had these pipes, this connecting each segment, I needed to transmit power from one segment to another. I needed to run wires. And I didn't know how to do that. I thought maybe if I had these rigid pipes between segments, I could transmit the wires that way. The other thing is that for strength reasons, I had put stops. You can see that right here and right here are stops so that when the thing turns, those hit. And that's very important because if I didn't have that stop and I used the ball joint itself to stop the motion, you get a large bending moment on the ball joint and snap it off like breaking a stick. Whereas instead, what happens is the forces go through this stop and put these stops into compression, put my ball joint into tension, and have a large distance for the moment to be resolved. So the actual forces involved are much lower for a given torque. And that worked very well there. It also works when you bend up. The tops can crash. But since this is a vehicle that has to drive on the ground, I couldn't hang stops way out here because they drag on the ground. I needed the high ground clearance. So I was in danger of having that breaking it like a stick over your knee effect this way. And that's another use that these orange pipes serve, is that they go into tension when you are at the limit of your motion. So it's kind of a multiple use. One of the main design issues during the development of this thing was how do we make it strong enough, apart from all the other design issues. The types of things you're looking for when you're developing something like this is you've got to meet safety requirements. You're trying to make the cost. The way to make something cost invariably is to make it light. Weight is the biggest, in terms of the plastic, weight is the biggest determining factor of cost. A large thin-walled part can be as cheap as a small thick-walled part. So let me just put you where we are in the timeline right now. Mid-July maybe is when we first started looking at it, and we did some breadboard development around here. By breadboard, I'll show you what I mean in a second. But a breadboard is basically a crude model that is used to prove a principle, demonstrate feasibility of something. Early on, we did a preliminary cost estimate. So right around here, I put together real rough sketches and guesses on piece count and the bill of materials on what it would take to build one of these. I hadn't even built one yet, but I'm guessing what I think it'll take to build one because we want to know if we're in the ballpark cost-wise. And so I just made rough, I made sketches on the order of, this, and said, okay, that's the, that's the segment, and I gave a rough, that's 3 inches, etc. Just so that, and a wall thickness, just so that the factory could take a guess at how big of a tool would be required and how much plastic this might have, etc. And so they got the cost back around September sometime. The culmination of the breadboard development was the running breadboard model, which was, again, based on these components right here. So we used these components, duplicated them using a casting process, and wound up with a breadboard that we could run. Now we're on the roof.
Rollover be good.
New York City.
Yeah, really critical. That'd be great commercial.
Oh, I missed a good part there.
The wheels?
Yeah, right, left.
The other wheels? Almost beat it over. Rollover be good. Yeah, really critical. That'd be great commercial. This guy pulled out. Ooh, that didn't sound good. I didn't like the sound of that one at all.
That bent over at the bottom.
The head-on stops don't help you any. Yeah, well, it's gonna roll much better with the cool. Okay.
We can accommodate that.
Yeah, sure. Can't get too much far here. To make it more stable and it works.
Yeah. That's cool because it straightens out and it's just enough that the back end whips a little.
The back end is feeding into it, pulling it off, but then the front grunts and just drags the back where it wants. It doesn't, the front is winning now.
How a lot of the point of a breadboard is to do the movement.
Okay, it's documented. It can climb an orange.
So that's what a breadboard is in its purest form. Once we had gotten that breadboard finalized, the idea was to now go into engineering, because the beautiful thing about the breadboard, I'm designing this thing in Pro Engineer, and the beautiful thing about the breadboard is that you've established the design parameters that are the most difficult to think about when you're in the computer. When I'm sitting there looking at this on the screen, I don't know how fast it's going to go. I don't know what gear ratio is right. I don't know if it's going to be able to climb an 8-inch block. I don't know any of those things, and I don't have time to use the software that might be available that could predict that if I was really lucky. You know, FEA software or dynamic analysis software, all that stuff, it takes weeks and weeks and months to come up with a solution, and the solution's only as good as the data you give it. I don't know exactly what the friction is in here. I don't know the exact specs in that motor. I'd have to do testing on the motor to determine the property, all that stuff. So there's nothing like a breadboard to cut through all that and in a matter of a couple of weeks or less, find out, can it climb the block or not? And if it can't, then you change the gear ratio and try it again. And that's what we were doing on the roof there, was finalizing those things. So now once those things are finalized, I can go on the computer, take those gear ratios, and get them any way I want. I might have used 4 gears in the breadboard, and if I can come up with a way to use 3 gears in here and get the same ratio, great, more power to me. But I know what ratio I'm shooting for, and wheel diameter, all that stuff. So, so the beautiful thing is that I can sit there with confidence and design something in my computer that I know is going to work. If I can get it at a certain weight and if I match the parameters that I established in the breadboard. So I spent about 6 hellacious weeks because I had the feeling this was like such a cool project. I hadn't had anything this cool, done anything this cool since I worked on the car team. And I'm like, this is a once-in-a-lifetime opportunity. So I was really, really pumped for it. So I spent like 6 weeks, 7 days a week of 10-hour days, ridiculous stuff, trying to, because we were very late on this schedule. So I did engineering maybe from here through to the beginning of November. And once engineering was complete, we go to prototypes. And we use this stereolithography process to create samples of every part in the toy. It cost about $20,000 to grow all those parts. And that took about 2 weeks. And then we used a model shop to clean them up and duplicate them and make castings. This is an example of a casting of one of the segments. You can come and look at it later. And based on those castings, we were able to build a sample that looks just like what it will look like when it's produced. This one has a lot of wear and tear on it and isn't the right color, but this is a cast sample. And it's decorated properly. It's almost indistinguishable from the production unit. But this cast sample is available at the beginning of December because we're trying to shoot a TV commercial that we can edit and have happy in time for a trade show in late December, and then certainly we need it in time for the February Toy Fair. But there was a show in December, maybe that was Hong Kong Toy Fair, I'm not sure, that they were shooting for it. So right around, so from like here to here was the model stage, and then right here is TV. Shoot the TV commercial down in Florida in about a week. And we used those samples to do that. We never used that shot in the final commercial. We took a competitor item, the Fast Track at the time, which was the hottest RC car, and we spray painted it blue, took the labels off, and showed how we could, nothing could stop the Brute. And speaking of the Brute, we were trying to name this thing. The code name for it originally was Sidewinder, which is a cool name for this truck. And our company had rights to the name Brute. We had, every stupid truck we had in our line was called Super Brute, Mini Brute, Big Brute, Little Brute. It was sickening. And we in R&D, I'm an engineer R&D / everything guy there at that company. We didn't like the name Brute. We didn't think it was we didn't think it was a cool enough name. And our CEO, who's from Canada, thought it was great. And I was like, is this something to do with Canada? Do they say, Wayne Gretzky was a real brute yesterday on the ice? I don't know, but I think it was more expedient. He just liked the name Brute, or he liked the fact that he didn't have to pay for another name or fight somebody in court for it. So they called it the Brute over all of our protests, and here's the first cut at the commercial.
Watch out! It's the Brute! The Brute! Nothing can stop the Brute! Radio control, 9.6 volt power. The Brute! 10-wheel speed, 10-wheel power. Never before. The Brute! It grabs, it climbs, it flies. The Brute! Brute speed, brute power. It's brutal. The Brute! Nothing can stop the Brute from Buddy L.
Now, finally, they took this out to show it to some buyers, and there was one buyer who said, I will absolutely not buy this product if it's still named the Brute. And we all cheered. So,
it's the Rattler 10WD. Nothing can stop the Rattler. 9.6 volt power. 10-wheel speed, 10-wheel power. Never before. It grabs, it climbs, it flies. The Rattler, brute speed, brute power. It's brutal. The Rattler 10WD, only from Buddy L.
There you go. It's brutal. So, so at least we got it to not be named the Brood. You know, we had nothing to do with it. So that was the culmination of the engineering, of the bulk of the engineering phase. But we did a lot. I'm at the TV commercial. We had like 5 samples, and we have 4 of them broken at any given time. So I'm trying to fix the broken ones, and they're saying, you know, we need a Rattler, you know, we need a Brute in 3 minutes. And I'm like, I'll do it. It'll be there. And so we just about give me the broken one that they just broke, and I give them the one I just fixed, and we keep going. And so we learned a lot, thrashing them and driving them around, and we had a few minor changes and refinements that we wanted to make based on what we learned there. So spent maybe a couple more weeks finalizing the engineering and putting together a turnover package. So right around here is manufacturing turnover. I forgot to mention that in the middle of the engineering phase, we did another cost, which was because the first cost was so out there in terms of I had no idea what it was going to be yet. Whereas halfway through the engineering phase, I hadn't solved all the problems, but I had fleshed out the basics of what the product was going to look like. Now at this phase, by definition, when you turn it over for manufacturing, you're getting a final quote on the project. So we're sending this to our Hong Kong office. They're bidding this to maybe 2 or 3 factories. They're Hong Kong-based Chinese factories, and they will tell us, give a breakdown of what all the parts are going to cost, assembly, tooling, everything. We subcontract everything to them. They take care of getting the tools built and everything. So at this point, you get your final quote, and then you release the tools. Once you approve a quote, you release the tools to be created. So I just wanted to, now that we're getting into the manufacturing phase, I just wanted to address some of the issues that one deals with when thinking about how to make something manufacturable. You have to take into account the technologies that are going to be used to make the parts and the types of factory or facilities that are going to be used to assemble the parts. And you have to design your product to work within that framework. So there's almost a vocabulary of toy technology that you can use. For instance, that's why I said a speedometer cable driving the wheels is not toy technology. It's something you find in a car, not in a toy. You know, what are you going to use? Little brass collars with set screws to make the worm gears onto the shaft. I mean, it's ridiculous. It's got to be much more basic and cheap than that. So you've got to take into account the fact that you want the parts to be injection molded. Injection molding is the cheapest way in volume to get a shape in plastic. There are a bunch of different technologies that you have available to you to get a plastic part. You can use vacuum forming, which shrinks. It's like a shrink wrap kind of effect where you shrink hot plastic over a form, but that is very slow, and it requires a lot of post production work. We have to trim off the excess and things. You can't get a lot of detail into it. Next up, you could use something like blow molding, which sort of inflates a balloon of plastic inside a steel cavity. That also tends to be fairly slow and has some work you have to do afterwards. And injection molding is sort of at the top of the heap in terms of high-speed production of parts. But as the cheapest in volume, the upfront costs are fairly large. On this product, there was about, let's say, $50,000 in development costs between building the models and sourcing various things. The tooling cost about $400,000 to make the steel tools to build this product. There's a lot of parts here, and so there's a lot of big blocks of steel needed to make all these parts. And the TV shoot, filming TV commercials cost maybe $500,000. They spent maybe $2 to $2.5 million on media. That means buying the time for the commercial. The unit price of the toy is maybe $20, $25, and they're looking to sell 300,000 or 400,000 of them. So, you know, you're looking at $5 to $7 million that you have to put up to buy the initial to buy the toys before you get paid for them by the retailer. Because the toy company has to buy the toys from the toy factory and send them to the retailer and then wait till December to get his money. So you've got to put all that money up front. So the total capital investment required to get something like this off the ground is pushing $10 million. Just to give you a feel for the numbers. And that's why toy companies often operate at a loss for 3 quarters and then make up the difference in December, particularly if they're a very seasonally driven company. That's why companies try to diversify and have summer goods as well as spring items so that they're not always selling everything in the 4th quarter. Because then they have to go into tremendous debt for 3 quarters and then tremendous riches for 1 quarter and pay off all their debt. So my goal is to try to utilize the technologies I have available to me. And the other thing is that I just want to back up 1 second. There's one general principle back in this stage that I forgot to mention. When we're marketing is telling us what they want the toy to be, there's a little bit of knowledge is dangerous effect that can occur where marketing people and salespeople can start learning some lingo, and they say, they learn about a certain type of Mabuchi motor, the Turbo Wine 3000, or a certain type of gears or whatever, and they start telling you, I think you should have the Turbo Wine 3000 and the Metalite gears and this and that. And what you have to be successful in a creative engineering type role, you have to learn to give them what they want and not what they ask for. That's the mantra. Give them what they want, not what they ask for. In other words, these people, the whole reason you exist is because these people don't understand how to make this happen. You understand how to make this happen. They're just trying to tell you what they want as an end result. But oftentimes they'll describe it with overly specific terms. And your job is to tune out the specific terms and read behind them and find out what they really want. When he says he wants a turbomatic motor, what he's really saying is he wants it to be powerful and fast. And so you don't say, oh, he told me to do a turbomatic motor. It's stupid, but I'm going to do it. And he told me. And then when it doesn't work, and I say, hey, but it's because I used a turbomatic motor, and that's what you said. You know what they're going to say. Don't get technical with me, something like that. So the point is, to be really successful in a creative job where you're trying to interpret marketing and sales requirements in a technical product, is to try to figure out what they're asking for and not listen to what to figure out what they want and not listen to what they're asking for. You got to read behind what they're saying. So that's one of the keys. So at this phase, we're trying to design the product to be manufacturable. In this case, we've got injection molded parts and a bunch of purchased metal bits that are going to try to come together and be a working toy that's going to do everything that it's supposed to do. Can't use speedometer cables and things like that. Some of the issues here you have to deal with is you have to think about how is this thing going to be put together. In the case of this wheel, you've got a gear, you've got a bearing on either side of the gear. Then that gear is in this little housing with the bearings. Then there's another housing that's out here. There's got to be another bearing out there, and then you've got this wheel pressed onto that shaft right there. So how are you going to get all that done? Well, the standard method is to knurl, take a round shaft and put knurls on it, which is a way to upset the metal to make it grip something that you press onto it. Well, the problem with knurling is that how are you going to assemble this thing? That's what you always have to think about. You can't just design the thing in your mind fully assembled. You have to think, well, how would someone physically put it together? And if it had a knurl on there, in order to drive this gear, well, how are you going to get that knurl past these bearings? And things like that. So I was asking myself those questions and not coming up with any answers. And the other thing is the torque is so high in this thing, you can wind up with problems where the knurling would just strip the plastic out. So the answer I came up with was to use hexagonal shafts. I don't know if that's clear in here, but if you can see that they flash the light there. So what the hexagonal shaft gives us, now the thing is that it's a compromise, because a hexagonal shaft is far more expensive than a round shaft. But by the time you put knurls on a round shaft, maybe it's starting to break even a little bit, but probably not. But by the time you take into account the assembly issues, the hex shaft wins hands down, because now instead of having to get past all these knurls and worrying about them breaking, you just have a hexagonal hole in this here, and you just slip everything together. And what they do at the end is they punch a little barb into the end of the gear and then slam the wheel on, and that locks the wheel. Another issue is strength and durability. These trucks, I'm not going to do it because I'm starting to run out of these, but these trucks are dropped from 38 inches onto concrete 6 times in random orientation. And they're supposed to continue functioning when they're done, and more particularly, not exhibit any safety problems. In other words, if I drop this and one of these segments cracks off, now we've got sharp things from the insides exposed. And then that fails a different test, like a sharp point test or a pinch test or something. So in order to pass a drop test, and almost even worse than a drop test, this product is designed to climb a cinder block or a thing like that. The wheels are the first thing that hit when you come up to an obstacle. And that's by design. So you can see that the wheels are prominent. But that means that the full driving torque of the motors, plus all the inertia of this entire system, plus the rotational inertia of all the wheels, is driving this thing into whatever it is that you just hit. And the assumption is that kids are going to drive this into brick walls regularly, and it should withstand it. So that's where another thing comes from. What I did on this is I designed the wheels out of a soft, flexible plastic polyethylene, which is great for absorbing impact and not breaking. This stuff will crush and crunch, but it's never really going to crack, and which is what is needed to absorb the energy of an impact. And I have a very thin, you can see it's a very thin tire over it, and that's to save weight. Instead of having a full tire, since we've got 10, on this whole program I was looking at weight savings, and anything I can do to save weight on the tires is very important because it's times 10. So it's got a very thin rubber tire. But the idea is that everything is a compromise and nothing is optimal. You've got this nice soft plastic which will absorb the impact wonderfully. But how are you going to transmit torque to your soft plastic? Well, you've got a hex hole in the hub of the plastic. But I just said it's nice and soft. So the hexagonal shaft is not going to key very well to it, and if you took it and just twisted it, you'd twist the wheel right off the axle. So the answer to that was to make a hub, that black hub, out of a hard, rigid engineering plastic. It's made out of an acetyl. So the hub gets a wonderful press fit onto the shaft, the barb digs in beautifully, and the hexagonal shape is locked wonderfully to the hub, delivering torque very well, and you're never going to get that hub off. And then the hub transmits the torque to the plastic, to the outer plastic wheel at a larger diameter, distributing the load over a larger area, so that the soft plastic can handle it. The other bonus that we got out of this is that I built in a clutch between the what's clutching in this one, between the wheel and the hub. And what the clutch does is the clutch isolates the gear train from the external world. In other words, say a kid takes one wheel in one hand and the other wheel in the other hand and twists them in opposite directions. That's going to wreak havoc if you have it rigid, because there's no way with a 3-inch diameter wheel that you're going to be able to be stronger than the kid. It's always a mistake in consumer products to assume they're not strong enough to break my product. I'm going to build my product stronger than they are. That's not a good approach. The approach is, I'm going to build my product so that if they try to abuse it, something just gives away in a controllable fashion. And that's what's happening here. This clutch is giving away in a controllable fashion at a marginally predictable torque. So, and it gives a lot of other benefits. It gives a benefit from the abuse. In this case, it also gives the benefit that when you do crash into that wall, maybe that clutch is going to pop a little bit instead of thrashing the gear train and popping these U-joints. We did have problems with U-joints exploding, and I had to strengthen those. This toy was a classic case of the weakest link in the chain theory. Once we let me advance in the schedule here. They build the tools. We had first shots in March. So right about here, we had first shots. We started the tools a little before January. The schedule's kind of a little bit wrong. The tools started around here. So first shots means, well, let me just, I have just about enough time. The idea of an injection molded product, an injection molded tool, I just want to express this very basically. Imagine you had a plastic mug that you wanted to mold. So let's imagine there's no handle on it. And so let's say the mug, looks like this. Now, in your mind, let's flip this upside down because that's how I want to mold it upside down. The way you could mold this is you have a core which is shaped like this on a block of steel. It's a lump on a block of steel. And then you have a cavity which I'll turn up so you can see it. The cavity has a hole in it, and then like that. So what happens is when this mold closes, this circle on the cavity is actually out here on the core. So there's a gap between this core and that hole, which is called a cavity. That gap is in exactly the shape of this cup. So what you do is you close the mold, you shoot plastic in, you open the mold, and you bang the cup off. And then you keep doing that, and you can do that like every 10 seconds. And that's why this is so cheap. But these big blocks of steel can get expensive, and it's not just a cup, it's the shape of that, so it's pretty hairy to machine it. Some of the basic principles of injection molding are that you have to have a draft on the part. You see how I made this tapered? That's exaggerated. You usually get away with like a half a degree or a degree. Because when the plastic shrinks, when plastic cools, it shrinks, so it tends to clamp itself onto the core and get stuck there. And so what they usually do is they have little pins in the mold which push up and actually bang it off the core. Now, if you try to put a handle on this mug right here, how are you going to do that? You can't just stick it on there, because if you close this mold and you had a little pocket for the handle, you filled it with plastic, plastic would run all around the handle, and when you will be locked to the steel, and that's what is called an undercut. An undercut is a situation where it basically prevents you from taking the plastic off the steel. So the whole design of the entire product has to be done with that in mind. The other thing about injection molding is they love flat parting lines. They like to have two blocks that are nice and flat, and then everything happens in there. And so those are the types of principles that I use in this product. If we look again, let's say at this is one part and that's another part, and you can see that the parting line is right there, where you see the two parts meeting. That's the parting line of the mold as well. So you can see that this thing is tapered that way. That's your draft. And then this one, everything goes the other way. And so that's how you get this spherical ball in two pieces. You can't do it in one piece unless you do real crazy molds. So the whole point is you're trying to do, trying to keep things simple. Because I want the tooling to be cheap. I want the tooling to be easy to make, because then the tooling is easy to fix and it's easy to run, and that's what you're looking for. So you have to understand. You have to understand the language of the factory that's building what you're doing. Do they understand how to do these types of assembly methods? Another issue is design for assembly. in manufacturing injection molded products, they like to do everything from one side. If you take any consumer product you have in your house, if you look at it, probably all the screw bosses are on one side, usually the back side because they're ugly. But it's not good practice to put like one screw here and one screw there and then one there and one there. The way this is designed is they build fixtures and they take all the top halves and they lay them down into these fixtures, and then they put all the components in, then they lay the bottom halves on, and then like a NASCAR pit crew, they punch in all the screws all at once, all facing them, nicely facing them. So that's another, design for assembly type issue that you've got to take into account. So then the thing, let's see, the thing was produced by the production pilot. After you get the first shots, then you finish the tool, then you have an engineering pilot where you take samples and put them together and see if they're going to work. Then you have a production pilot where you start up the production line, and then you ramp up your volume and start going. I'm out of time, so I'm going to wrap it up right now. What happened was our CEO disappeared about a year before the company went bankrupt. And once he was gone, his autocratic rule was missing, and they had found out that the commercial was not being very well received. It was a very cheesy commercial. The trade didn't like it. They wanted to do it all from scratch. So what they did is they asked me and one other guy to come up with a new idea for the toy commercial. And our basic idea was, well, let's get out of the way and let the ad agency do their job. But let's just tell them we want attitude. We want this toy to be seen as something that your mother wouldn't want you to have. And the other thing, guy had seen me carrying it like this, and he thought that would be a great way to start the commercial, would be to throw it down and then drive it away. And then I was thinking, skateboarders have this way of kicking their skateboard up. So I came up with this way, whoops, doesn't work with dress shoes, of kicking the thing up. And so we ended up putting that into the commercial, and I'll show you that right now. And on this commercial, I was the guy driving it off screen. The kid's got a dummy controller.
Meet the ultimate predator, the Rattler 10WD. In the world of radio control, its 10-wheel drive is virtually unstoppable. Powerful, quick, with moves no 2x4, no 4x4, no 6x6 can match. 10-wheel drive, 9.6 volt power. The Rattler 10WD, it's 10 times the RC. From Buddy Hell.
I like how he says Buddy Hell. Thank you, thank you. It's right there. My email address is right up here, and my webpage address is up here. Thank you. Thanks. Yep.